Welcome back. In this very important lecture, we are going to introduce certain new terms as well as bring a closure to the equations we have set up for handling thermodynamics. So let's see what we have in front of us. So in the previous lecture, we had addressed certain issues related to thermal and electrochemical combustion. This term electrochemical combustion might be new to you, but it's not very different from thermal combustion in some manner, and yet it's very different in some manner. Okay, so we had looked at enthalpy and Gibbs free energy changes related to combustion. So reacting systems are conceptually different from other systems because you do not have equilibrium. Okay, so things are always changing. So there is always entropy generation term. Okay, so this is what makes reacting system very different. And how once you have a certain amount of non-equilibrium, so how do you address the thermodynamics of such system is fairly complex. So I'll try to communicate, but I suppose there are other questions. We cannot take them up in the discussion on. So the entropy generation term is, if you, in certain condition, adiabatic condition, is the exit stream, which is entropy of the product, minus the entry stream. Okay, so entropy of the reactants. So that has to be greater than or equal to 0. How do you implement this statement in a balance equation involving entropy, which is, again, as I said, it's not a conserved variable, is what we addressed in the last lecture. We introduced this quantity called absolute entropy because the third law of thermodynamics states that the entropy of crystalline substances tends to be a constant as temperature tends to 0. So in most of the engineering tables, we assign that constant to be 0. With that as a datum, we specify entropy. Right? And we also addressed how to specify the entropy of mixtures of a particular component using the mole fraction of that component and total pressure and so on. So we addressed all these things in the last lecture. So get a feel for numbers by looking at the tables. Okay, so why are something 0? Okay, so these are standard substances in the standard state that turns out to be 0 here. But entropy is always a positive quantity. You can interpret this negative quantity in terms of chemical bonding changes, and then you can also interpret these numbers. Okay, so and so on. Okay, so all right, so it's important that the tables make sense for you. Okay, so by now you should be able to read all these tables. They are going to be extremely useful. And then we ask this important question of what is the work potential of chemically reacting system. For this, we started with, let's say, the exergy of the reactants and then exergy of products. And we looked at the chemical reaction being conducted at constant temperature and pressure. And the decrease in exergy potential is because of entropy generation. And then we asked what is the maximum amount of reversible work that can be obtained when the reactants get converted to products. So to do this, we started with the exergy balance equation of that was previously introduced when we addressed exergy balance. And then we, with some simple rearrangement of equations, we arrived at an important relationship the maximum reversible work that you can obtain from a reacting system is this quantity. Okay, so total number of moles and molar free energy gives free energy per unit mole, and then you can get this number. Okay, so what is the, so see, you have to understand how this is all defined. Okay, so even though we have a system not at equilibrium, the maximum reversible work can be obtained if the reaction is conducted reversibly. What do you mean by that? If the reaction is conducted at an infinitesimal rate. Okay, so if the rates are 0, and if you can convert all the or rates are near 0, if you can convert all the reactants into product in this reversible manner, then you get the maximum reversible work. Okay. However, in reality, the reactions are not conducted in this manner. They're conducted at a finite rate. So the work you get will be less than the maximum reversible work. Okay, so you have to understand even for a chemical reaction, you can have maximum amount of work as well as work that is obtained that is less than the maximum amount of work. Because of what reason? Because things change at finite rates. Okay, so what are the things we are talking about? The rates of chemical reaction are not infinitesimally slow. They happen at finite rates. So the maximum work that you can get is less than this work. And this, where do you see this kind of work? Many times when you think about chemical reaction, you think, let's say, some exothermic reaction, heat is transferred and so on. That's true, but you can also get work transfer. And the best way to think about work transfer is via a fuel cell. You run an exothermic reaction, let's say in a battery or in a fuel cell. This exothermic reaction, the delta G of the exothermic reaction, can be obtained, can be utilized for obtaining electrical work, right? So the energy conversion of what to what, the chemical energy conversion to electrical work in a battery or in a fuel cell is not limited by Carnot limitation. Okay, so it's important to understand that. That's why there's a lot of emphasis on energy conversion via a fuel cell or via a battery. So we looked at the most common fuel cell, which is the hydrogen fuel cell, PEM fuel cell, that's proton exchange membrane fuel cell, or polymer electrode membrane fuel cell. So here the exothermic reaction that's of relevance is H2 plus half O2 giving H2. Okay, so it has significant exothermicity. So depending upon the exothermicity, the open circuit potential that can be obtained is different. Okay, so the more the exothermicity, greater is the open circuit potential. Even for a lithium-ion battery, the similar principles are applicable for a lithium-ion battery. The greater the delta G, that is, if the delta G is more negative, the potential that you can obtain from a battery is more positive. So this fuel cell has its own challenges. The components might be expensive due to use of noble metals like platinum, ruthenium, and so on, or a membrane, which is Nafion membrane, which is a monopoly of a particular company. So lots of work is being undertaken to replace all these components, and it has other challenges. One is that hydrogen is a gas, right? So it's hard to store. So there are other kinds of fuel cells, let's say, which use methanol, but the exothermicity of such a reaction might be lesser. Therefore, the potential that can be obtained is lesser. So what is the difference, main difference between a battery and a fuel cell? A fuel cell is like a flow reactor. reactants come and flow out of the system all the time. Okay, so you can, as long as the fuel is being supplied, you can have a potential. But in a battery, it's like a batch reactor. You have some finite mass, and then they get converted, and the battery gets discharged. And if you have a rechargeable battery, again, this finite mass has to be, finite reactance has to be regenerated. That's what you mean by regeneration, recharging of a battery. So all these things we saw in the last lecture. We move on. So we had this general constraint on how do you define equilibrium using second law, right? So ds of a system is greater than or equal to delta Q by T. So there is a way of interpreting this. That's I always find the microscopic interpretation of entropy is more physically, the interpretation is more straightforward as a physical significance. In any case, this is a constraint, mathematical constraint from the second law. We want to see how we can extend this, generalize this to a chemically reacting system. So what is the reaction, for example, we are addressing? So let's say you have carbon monoxide plus half O2 giving CO2. Okay, so this is partially oxidized carbon. This is completely oxidized carbon. This is actually an important reaction because carbon monoxide is a poison. So, this is, in principle, this is attempted. Okay? In many times, we want this to be very efficient. So, the question we are asking is, if you have this reaction going on, what would be the condition for chemical equilibrium? If you look at the second law, we had framed the second law in terms of an external condition, right? If you have an isolated system, let's say this is an isolated system, the entropy will always tend to increase. Okay, so at equilibrium, the changes in entropy will be zero, but the entropy will tend to increase. So supposing I plot the entropy as a function of conversion. This is the entropy of the system at zero conversion. This is entropy at maximum conversion. Let's say everything is, let's say, products. So if the entropy changes in the following manner, the entropy will keep increasing till you get an equilibrium composition, which will be less than that of 100% conversion. Why? Because the entropy of this at this point, that is 100% conversion, 100% product is less than the entropy of system with this composition. So based on the second law, that the entropy will attain a maximum value, that is, the entropy will be the highest at equilibrium, we can establish equilibrium composition. Right? So this is useful, okay, this is conceptually useful, but practically this is not very implementable because we have to be always checking for heat transfer and things like that, okay, from the system. Right? Just to clarify, when I said, yeah, so in a sense that, yeah, so we will clarify the next, it will become more clear, the statement I'm going to make. So whether it is experimentally implementable is this question. Okay, this is not very easily implementable. We'll see why, because experiments are often conducted in a different manner by controlling different aspects of the system. Okay, so for example, if you have, let's say, a control mass, and this reaction is conducted at constant temperature and pressure. Why? Let's say this is, let's say, a solid. It can be a phase equilibria of an alloy. The temperature is that of the ambience. The pressure is that of the ambience, atmospheric temperature, atmospheric pressure. Okay, so that's the condition that I can control. And then there is some heat that is being released, and let's say there is expansion work or some work that's being done. you want to have the condition for chemical equilibrium. So how do we go about doing this? We first write the first and second law. This is the version of first law that is relevant to this system. And this is the second law constraint. When you combine both of them together, you can write it in this manner. Here, in a way that we addressed enthalpy, for example, or you've done a homework problem also, we can rewrite the entire, all the quantities of relevance in terms of Gibbs free energy. Gibbs free energy change is G is equal to H minus Ts. So dG is equal to Th minus T ds minus STT. And then when you simplify this further by incorporating dH in this manner, because the system is at constant temperature and constant pressure, these two terms turn out to be 0. So dG is equal to this particular term. So all I'm doing is, instead of using these three terms, I'm going to call these three terms together as dG of the system, right? Because that is really the Gibbs free energy of the system. So note, what is that we have controlled? We have done this experiment by controlling temperature and pressure. At constant temperature and pressure, what is the natural thermodynamic function to address is the Gibbs free energy. So at equilibrium, the extremal condition is dou G is lesser or equal to 0. That is, the Gibbs free energy will tend to decrease. Okay. So at equilibrium, it will be, the changes in Gibbs free energy will be 0. So if I plot it, I will have this condition, right? Dou G takes a minimal value at equilibrium composition, and supposing 100% products has greater Gibbs free energy, you won't be here. Okay, so you would only be able to reach this composition which defines equilibrium, right? So it's important to understand why we introduce Gibbs free energy. Okay, so we had a situation where using entropy was conceptually all right, but practically not implemented. Okay, so we transformed this into another thermodynamic function, which is Gibbs free energy, because we are conducting the experiment at constant temperature and constant pressure. Okay, so that is the reason why we introduced this new thermodynamic function of relevance here. So again, we get an extremal condition for defining equilibrium. So let us implement this on a model chemical reaction. So we have A and B reacting to give C and D. So let's say DNA. So it is an extensive quantity. So some differential change in Na reacts with the differential change in B to generate differential change in C and differential change in D, right? I'm just implementing the condition that is derived in the previous lecture, in the previous slide, implementing that constraint in terms of sum of changes in free energies is equal to 0. How am I writing these free energies? It's important to understand this point. Okay, so this is molar free energy, that is the total free energy divided by the moles of the substance. Okay, this is an intensive quantity. Okay, this is an extensive quantity. So this molar free energy is also called chemical potential. Okay, this is a very, very important term. It is usually in all other textbooks we use this symbol called mu. Okay, so in the textbook of that has been recommended, we use a slightly different symbol, but that symbols don't matter. So this is the chemical potential. So the dG of a particular component, I write it as an intensive quantity times the extensive quantity. This involves the total number of moles that is being changed. This is the chemical potential. Total free energy divided by the total number of moles that is present of that particular component. So I write this dG, and then I implement this constraint. Okay, sum of free energy changes has to be 0. And then I'm going to rewrite this in a slightly different form. dNA, I write it as minus epsilon times nu A. Okay, so this is called the extent of the reaction. Nu A is the stoichiometric coefficient. Okay, so these are dNA is the number of the change in reactants, so that will be decreasing. So that's a negative quantity. These are positive quantities because that's increasing. So this epsilon is called the extent of reaction. These are the stoichiometric coefficient. When you apply this to a specific system, it will become more clear. When I put these things into this is just mass balance, I will have this quantity. Epsilon gets cancelled because extent of the reaction gets cancelled because it appears in all the 4 terms. These are the stoichiometric coefficient. When I implement this in a specific system, it will become more clear. So supposing I have H2 giving to H. If I have 0.1 H2 reacted, I will generate 0.2 H generate. Okay, so new H2 is 1 and new H is 2. Okay, these are the stoichiometric coefficient. Okay, what precedes this H2 or H, right? So, okay. So when I plug this form into this form, I get the criterion for chemical equilibrium. Okay, so this is a very, very important criterion, right? Written in a slightly different notation. This notation, as I said, people use mu. Okay, the Greek symbol, which is like U. It doesn't matter. So the criterion for chemical equilibrium is stoichiometric coefficient. These are the stoichiometric coefficients. The corresponding chemical potential summed up for all components has to be 0. Okay, so all right, so this is a criterion for chemical equilibrium. So there are, when you say thermodynamic equilibrium, there are 3 equilibrium that is of relevance. We started with mechanical equilibrium. Even before coming to this course, from mechanics itself, the condition for mechanical equilibrium is obvious. You've done that in earlier courses. Then we establish the condition for thermal equilibrium, temperature being the same. Then the third part of equilibrium is a chemical equilibrium. The constraints have been derived in this lecture. How do you implement this for a real system? Again, so you use the approximation of ideal gas. So obviously we are talking about a gas mixture, and you consider the system to behave in an ideal manner just for pedagogy. Okay, so this is easy for treating the class material, but in principle, you can also use more accurate expression. So if you have an ideal gas system, we are doing this chemical reaction at constant temperature. So delta H changes is 0. So all you have to think about is entropy changes. So you use the ideal gas expression and you get the change in chemical potential in this form. So this, you must be familiar by now. How do you do this kind of manipulation? And we write this free energy chemical potential change in this manner. What is this? There is, I can split it into two parts, right? One is at a standard pressure, let's say 1 atmosphere, and then the other component is at a different pressure. Okay, so I'm interested in the chemical potential at temperature of relevance at which the reaction is conducted, and at a particular pressure, but I document all these values with respect to chemical potential at some standard pressure. That standard pressure is, say, let's say 1 atmosphere, and then there is this other component. And then you know how you define RU and so on, right? All right. Okay, so that's the way I'm going to define the chemical potential. I'm going to plug this form into this expression. I get this general expression, reaction coefficient times the chemical potential for that particular component, summed up for all components is 0. I'm going to further manipulate this, pull out all the chemical potentials at the standard reference pressure. Okay, I am going to pull that out, call that as delta G star. Okay, so and then I'm going to write something, split this entire equation into this component plus the rest of the components. So if I plug this into this general expression, I have delta G star is equal to RT and this form, right? So this is the equilibrium constant. Okay, this you've seen from high school, equilibrium constant of a chemical reaction, chemical equilibrium constant. I can write it in terms of concentration that you do it for if the system is in, let's say, in the liquid phase, but in gas phase, you typically write it in terms of partial pressure or mole fractions also. Okay, there are different forms. So the form which we are using is in terms of partial pressure. The other two forms which you must have seen is in terms of mole fraction or in terms of concentration. When I write it in this manner, the chemical equilibrium constant. So when you say constant, it's a constant at a particular temperature. Okay, so when you change the temperature, the chemical equilibrium changes. It gets shifted. Okay, it's a chemical equilibrium constant only at a particular temperature is equal to this particular quantity. I can write the partial pressure in terms of total pressure times mole fraction. I can get this expression. Then I can have an expression for the chemical equilibrium constant in terms of the overall change in stoichiometry, total pressure, and then total number of moles. Okay, so this is the mole fraction expression also. So you might have seen another expression in terms of mole fraction or concentration. You can these are all simple rearrangement, but here we are dealing with gases, so we are writing it in this form. This is a very important expression because you have seen this from high school, but in a form where the basis was not clear. Okay, the form you've seen this in your high school is called the Chatelier principle. Okay, how does the equilibrium change for an exothermic reaction or an endothermic reaction, or when there is decrease in volume and so on, right? So all these conditions you've seen, and you called it as Chatelier principle. Okay, so as you progress in your understanding, you will see the basis of many different laws is one and the same. Okay, so you will have fewer and fewer laws, and the consequence is what you saw as a different law. Okay, in the Chatelier principle, you were You had seen this in high school, but probably it was not derived, okay? But you utilize the Chatelier principle, for example, in ammonia synthesis, which is probably one of the most important chemical reaction wherein Chatelier principle has great consequence, because ammonia synthesis is important for fertilizer generation. It revolutionized the chemical industry and food supply for the entire world population. So you might have seen that in that context, but the basis for Chatelier principle, or it's a French name, is clear from the thermodynamic derivation for Chatelier principle. We derived this using the criteria for chemical equilibrium. So del nu is the changes in stoichiometric coefficient. We will derive another important relationship, which is again an aspect of Chatelier principle, which is the change in chemical equilibrium as a function of temperature. So in the previous slide, we had derived this equation. So what we are going to do is that express delta G as H minus Ts. So I am asking the question, how does equilibrium constant or chemical equilibrium change with temperature? Okay, so I'm differentiating ln Kp by dt to ask this question, how does Kp change with dt? So I'm just differentiating these three components. How do you simplify this? Go back, whenever you see changes in ds, go back to T-ds relationship. Those two T-ds relationship are very, very important. Okay? You should just commit them to your memory. So I use TdS is equal to dH minus VdP because these reactions are conducted at constant pressure. This term turns out to be 0. Therefore, I can write TdS as dH star. Okay, so this term is this term. This term is this term. So these two terms cancel out. So we are left out with only these two terms. So when I do that, I can write in this form. Okay. So this is again the basis for Chatelier principle for exothermic reaction and endothermic reaction, because delta H and delta H being positive or negative is what determines your whether your reaction is exothermic or endothermic. And you had asked this question even at high school, how does the chemical equilibrium for an exothermic reaction or an endothermic reaction change when you increase or decrease the temperature? Okay, so the Chatelier principle was framed in a non-mathematical term using a statement. You go back to that statement from your high school and relate it to the mathematical form that has been derived here. Okay, so the goal of science is to unify, okay, to have few principles and derive the consequence, many consequences. Okay, that's the goal of science, unify. Okay, you might have seen and heard in physics called grand unified theories. Okay, likewise, we want to have very few fundamental principles and then look at its consequence. So Chatelier principle is just a consequence of this analysis. So typically you ask this question, how does the chemical equilibrium change at two different temperatures? So I just consider T1 and T2, and that depends upon H. I can rewrite this in a slightly different manner because dH by dt is related to specific heat capacity at constant pressure. I can then implement the delta H of the reaction in terms of specific heat capacity, right? So total delta H is the sum of reaction stoichiometric coefficient times the heat capacity. I can write it in this form. So this form goes by Kirchhoff's equation. Okay, so this equation is called the Van 't Hoff equation. This form of writing the same results is called the Kirchhoff equation. Okay, so these are all derived by different German scientists, but you can derive all these things from few general principles. Okay, so Germans and French and the British. Okay, most of the development of thermodynamics happened in Europe. Okay, especially in France, Germany, and England. The first place where thermodynamics developed outside of Europe was in United States when Gibbs started coming up with his formulation of thermodynamics. Okay, so Van 't Hoff, Kirchhoff, I think they're all German scientists. Chatelier was French scientist. Watt, James Watt was, I think, a British scientist. Right, so it's interesting to see the history of thermodynamics, how each concept led to every other concept. Many of these concepts are result of what can be measured in those times carefully. Okay, so there is yeah. All right. So we have wrapped up thermodynamics in some sus and present. Now we are ready to present it in some succinct form. Okay, so it's very important. This and next slide is very important because this brings in a closure into the laws of thermodynamics. We are presenting the external condition under different experimental conditions. Supposing you are able to control the entropy, suppose at the boundary, okay, control the total volume, control the total number of molecules, okay, then the thermodynamic potential of relevance is U. It takes up a minimum value, and du is expressed in this manner. Okay, so this is the term which we have introduced in this lecture. This is the chemical potential. This is the standard symbol that is used in all textbook. Somehow your textbook has a different symbol, but doesn't matter. So we had used G, which is the molar free energy. This is also called the chemical potential. Okay, so if you look at this expression, there is certain pattern. There is an intensive quantity, there's an extensive quantity. Intensive quantity, extensive quantity. Intensive quantity, extensive quantity. Product of this will give you something to do with energy. Okay, so in some way ds has something to do with thermal energies. Okay, so this is a minimum. Okay, the condition at equilibrium is this takes an external value, which is a minimum, right? So entropy takes up a maximum value if you can control UVN. This is an isolated system. That is, the total internal energy is a constant, total volume and N is a constant. Okay, these two are not the easiest way to conduct an experiment. I don't know how to control entropy, even though volume and N are total number of molecules are easy to control. Okay, so this is isolating a system is not very easy, but they have some conceptual and mathematical simplicity. Okay, so this what Boltzmann worked with. Later forms were derived by Gibbs and so on. So if you control this for an isolated system, S takes an external value, which is a maximum. And ds, again, I can write it as an intensive quantity times extensive quantity. Intensive quantity times extensive quantity. Okay. So difference in temperature, if 1 by T is different, it gives rise to entropy flux. If P by T is different, okay, it gives rise to entropy flux. In some ways, 1 by T, P by T, and mu by T are driving forces. If there are difference between two different systems that are in contact with each other, if temperature is different, therefore 1 by T will be different. there is a driving force, okay? There is a flux as a consequence of driving force. So 1 by T is a driving force, P by T is a driving force. This is connected with thermal equilibrium, this is connected with mechanical equilibrium, this is connected with chemical equilibrium. Okay, all these driving forces are intensive quantities. Okay, when two systems have a different temperature, there will be a driving force for equilibrium. Okay, there will be a driving force for flow of fluxes, which will tend to get both the system towards equilibrium. Then you go to other ways of conducting experiment. Again, this is not often seen, but these two are becomes more and more usable. The experiments are most easily conducted in this manner by controlling T and P of atmospheric temperature and pressure. Again, G takes a minimum value, and this is the condition we derive in this. Okay, so corresponding to different ways of conducting the experiment, the natural variable is different. Okay, so what do you mean by natural variable? The natural variables for this thermodynamic function are these things, which are controlled at your boundary. What the system variable that are controlled, constant T, constant P, constant N, gives rise to a maximum of a particular function. Okay, G. Okay, so don't get confused by the zoo of quantities. Okay, there is a variety of quantities that we have derived. Okay, we have introduced, but there is a conceptual simplicity to view these different thermodynamic functions. This table I've taken from a very good textbook, Molecular Driving Forces by Kendall and Bloomberg. Extremely conceptually very clear with beautiful drawings and so on. And so you should, if you're interested in this subject, you should take a look at this subject. Maybe it's at an advanced level. It is offered as an elective in many of the departments. In chemical engineering, we often this course every year, sometimes twice a year also. When I taught this advanced course, I used this textbook. All right, so we derived a variety of thermodynamic relationship. Again, this material is just cut and pasted from this textbook because I didn't want to change anything because it is so well presented. So in the previous table, we derived different relationships, right? So these many different relationships we derived, okay? So these are fundamental equations of thermodynamics, okay, presented in this particular form. G with this particular variable, F with this particular variables, and so on. Okay? These are the fundamental relationships. These are fundamental and useful, okay? These 1, 2, 3, 4, 5 quantities, okay, are fundamental relationship. Here I'm able to define equilibrium in terms of an extremal quantity, okay, a quantity that takes an extremal value. We can, if you present U in this form, S in this form, H in this form, and so on, these are useful but not fundamental because take this form, U TVN is different from U as a function of SVN, okay? Only if you can present U in terms of this quantity, U takes an extremal value, okay? So if you present U in a different way, U will not take up an extremal value, but it might be useful, okay? But not fundamental. Why? Because if I want to present F, the natural variables for F is TVN. If you go back here, the natural variables for F, this is the Helmholtz free energy, are these quantities. Okay, so to present F, if you remember, go back to definition of F, okay? F is equal to U minus Ts, okay? So F is a function of TVN. in this case, U is a function of TVN. So I can use this for expressing Helmholtz free energy. Okay. In that manner, this is useful. Okay. But U presented in this manner is not going to be an external value. Likewise, I can also comment for other quantities. So there are useful expressions, but they are not fundamental expressions. Complete, but not useful. Okay. So if I have a table, let's say, of or an equation, f as a function of this, I can rewrite that equation or rewrite that table, present the table in a different manner. If I know f, if I have an extensive tabulation of f in terms of these three quantities, I can of course present t in terms of these three quantities. Okay, this is just a rearrangement. It is complete. Okay, all information is present, but not useful. Okay, neither useful nor fundamental. Okay, useful in the sense that it's not going to help me express some quantity in terms of an external quantity. Okay, it is complete, but it's not very useful. Okay, especially because I also don't know how to constrain or conduct the experiment by constraining f at the boundary. Okay, I don't know how to control temperature as a function of Helmholtz free energy V and N. Okay, so it's always important to keep asking yourself, how is the experiment being conducted? Okay, so that's an important thing you should try to understand. Okay, so that will bring you to that will give you a sense for why we present the laws and equations in a particular form. And then there is another set of relationship which is incomplete. So if you look at this relationship, supposing U is presented as PVN, okay, these are conjugate variables. Okay, so what do I mean by conjugate variable? T and S, P and V, mu and N, these are all conjugate variables. Conjugate variable come in pairs. One is an intensive quantity, another is an extensive quantity. So these are incomplete representation. Okay, so these do not uniquely specify the state of the system. Okay, so you have to really spend some time in looking at these equations, maybe even committing these equations to memory, and then digesting this information that has been present. Again, as I said, I took this thing without changing anything because it's so well presented in this book by Dylan Brugler. So as I said, this is a very important lecture, brings in a closure to many of the things which we discussed in thermodynamics. So in the next lecture, we will do one more topic, address one more issue of phase rule. We've already utilized phase rule in the early part of this course, but we will just address few other aspects of phase rule in the next lecture.